All right, here we go. Example 5. So I'm looking at this funky problem here. And you're thinking, okay, how convenient. The numerator factors into x minus 2, x plus 2. The denominator is just x minus 1. So you go, oh yeah, this is simple. The vertical, nobody canceled. So the vertical asymptote is just the 0 of the denominator. So that's x equals 1. The horizontal asymptote is we look at our horizontal asymptote rules. The degree of the numerator is greater than the degree of the denominator. Oh man, that means it doesn't have a horizontal asymptote. This was case number 3. Degree of the numerator is greater than the degree of the denominator means no horizontal asymptote. So then we got to say, well, does it have a slant asymptote? Well, the degree of the numerator has to be exactly 1 more. Degree of the numerator is 1 more than the denominator. And sure enough, this does fit the condition for a slant asymptote. And then somebody says, oh no, how are we going to find it? Okay, here's how we're going to find it. We have to divide the numerator by the denominator. Which leads me to, oh my gosh. We're having to do division. Okay. So one person says, all right, this looks like a problem we can do with synthetic division. This looks like a problem we can do with synthetic division because that would be 1, 0, negative 4, and 1 goes on the outside. So 1, 1, 1, negative 3. All right. And then, oh no, I'm going to get upset because I've got x plus 1 with a remainder of negative 3. Oh no, it didn't go in evenly. It's not supposed to go in evenly. That's the whole point. It doesn't go in evenly. If it went in evenly, it would have canceled. If this had divided in evenly into this, then there would have been an x minus 1 on top, and it would have canceled out. It doesn't go in evenly. It's not supposed to. And then somebody says, well, how does this make a slant asymptote? Well, here's what we do. We just drop the remainder. Instead of putting that negative 3 over x minus 1 as part of the answer, we drop it. And somebody says, how can you just do that? Because they're not supposed to be equal. They're not supposed to be equal. It's an asymptote. You are infinitely close to it. And if you think about it, this remainder part is the part that makes them infinitely close. Because as x gets bigger and bigger, if x is 10, and then x is 100, x is 1,000,000, x is 1,000,000,000, this number gets smaller and smaller and smaller. So the difference between this asymptote and the original function gets smaller and smaller and smaller as this gets smaller, because they don't actually touch. They just get infinitely close together. Just for the record, somebody else says, no way, man. I want to do this with long division. And sometimes it's kind of easy to do with long division because I want to make this point about it. I want to make this point. Since I don't care about the remainder, check this out. So I'm going to do long division. So x squared divided by x. So x times x is x squared. X times negative 1 is negative 1x. So now we subtract. So canceled. So I have 1x minus 4. So it's 1x divided by x. So that's 1. See, what happens is I can actually stop here. I don't have to do the whole division. I do not have to do the entire division because I don't care what the remainder is. So what I always say is this really just amounts to like a step and a half of the long division. Or you can do if your divisor is first degree, you can do synthetic division when you're finding the slant. But I concede slant asymptotes are a little bit annoying, and the whole problem is going to be a little bit more annoying from here on out. So let's keep going. Okay, x-intercepts are the zeros of the numerator. So the zeros of our numerator are the 2 and the negative 2. Zeros of the numerator. Y-intercept, what happens if we put 0 in for all the x's? If I put 0 in for all these x's, I get negative 4 over negative 1, better known as positive 4. Okay, point of intersection. We already hate point of intersection, just doesn't get any love. Now it's going to be worse. So the point of intersection, I take my graph, I take my function that I'm graphing, and I'm going to go ahead and use the unfactored form, the standard form, because I'm going to have to solve for it. and set it equal to my point of intersection. I'm sorry, set it equal to my slant asymptote this time. So this time I have to use the slant asymptote, okay? Because that's what we're trying to decide. Are we intersecting, it's either the or the slant asymptote. Are we intersecting either the horizontal or the slant? So if I try to solve this problem, I have x squared minus 4 equals x minus 1 times x plus 1, because I'm cross multiplying, just cross multiplying. So x squared minus 4 equals x squared minus 1. Hey, how convenient. All the x's cancel. So that means there's no solution right there. Okay, so no solution. So that was easy. In this case, it's a hassle. It's a hassle, but we had to do it. Okay, holes in the graph. Is there any factor cancel? Is there any factoring and canceling here? Nope. So there's no hole in the graph. All right, domain and range. We'll talk about that after we sketch this graph, because this is annoying. So here we go. I've got the vertical asymptote is at 1. Okay, there's no horizontal, but the slant asymptote x plus 1, which means I need to go back to my algebra 1 days. So the y-intercept is 1 and the slope is 1. So it's going to look roughly approximately like this. So there's your slant asymptote. You've been doing those since you're little kids. Let me see. The x-intercept is 2, 0 and negative 2, 0. The y-intercept is at 4. 1, 2, 3, 4. There's no point of intersection. That saves me a little bit of trouble. And then somebody yells and says, no, what does the graph do? Do I have to do 1,000,000 test points? I would say, no, you don't have to do 1,000,000 test points. If you want to do 1,000,000 test points, you can. Like if you want to say, well, what happens at 5? Like if I plug in 5 for x, well, if I plug 5 in there, that's going to be 25 minus 4 over 3. So 21 over 3 makes 7. So 1, 2, 3, 4, 5, 6. I just messed up. Let's start over. It's 21 over 2, which is not 7. 21, wait. 5 minus 1 is 4. Goodness, 5 minus 1 is 4. So it's 21 over 4, which is 5 1/4. So 5 1/4. So it'd be about right there. 5 1/4. Point being, it's below the asymptote. So you're thinking, okay, that's what we would expect. We would expect the curve to run inside the asymptotes. And if you wanted to, you could do some test points here. But at this point, we would expect the curve to run inside the asymptotes like that. Now, this would be a fair problem to ask you the domain and range on. The domain, we only have to exclude the vertical asymptote. The range, look at this. It goes down here all the way up to infinity on both sides. So the range is just all real numbers. Now, what's going to happen is we're going to have some problems where the curve is going to be on the inside. So later, I think on the homework, there's some problems where the curve is on the inside in here. Curve is on the inside. Well, we can't ask you the range on a problem like that because we wouldn't know the maxes and the mins. We'll deal with that later. But anyway, a problem like this, it would be fair to ask you the range. Usually on the test, when we get to this, we don't ask you the range anyway, because then that gives you a big hint about what the graph would look like. Anyway, so getting a little bit more complicated,